This screencast goes over the calculations involved in the iodine clock reaction lab. Recall that we are determining the rate law for this reaction. The S2O8 2- ion per sulfate ion reacts with the iodide ion I- and makes SO4 2- and I2. And then I2 will react with starch and produce the color that we use to determine the rate of reaction. Now remember that this reaction is coupled with a second reaction in which the I2 produced in the first reaction reacts with the S2O3 2- ion, the thiosulfate ion, to regenerate I- and also produce S4O6 2-. And we will use a small amount of S2O3 2-, and when that runs out, which will be when about 5% of reaction has happened, then the I2 that's formed in reaction 1 no longer has anything to react with other than the starch, and this gives us our blue-black color of the iodine starch complex. Up until that point, the color doesn't form because the thiosulfate ion reacts with I2 and prevents the iodine starch complex from forming and prevents the color from occurring. So we're going to use the initial rates method to determine the rate law. We're going to use the blue-black color of the starch iodine complex, and we're going to use the coupled reaction. And to do this, there's a number of things we have to talk about. One is if we compare, or if we look at what we're doing in reaction 1 or experiment 1, we're going to add 2 milliliters of the S2O8 2- ion, 2 milliliters of the I- ion. We're going to determine the initial rate, and recall that the other ions involved in the reaction either are essentially, for our purposes, they're spectator ions. We need them to keep a total ion concentration or charge concentration constant, but they're not necessary for the reaction, so we're going to not worry about them right now. And then the S2O3 2- does get involved in the reaction via the coupled reaction, but we'll address that in just a bit. So these are the volumes of the two major reactants that we're going to be using in the 3 different experimental trials, and we'll combine in one test tube. The key things are going to be I- starch and S2O3 2-. From the other test tube, we'll have S2O8 2-, and when they react, when they're combined together, they'll react. Color change won't occur until the S2O3 2- is used up, and when it is, we get that rapid appearance of the blue-black color of the iodine starch complex. Now note the initial molarity of the S2O8 2-, how it was made up is 0.200 molar. That's how it was made in the stockroom. But we're not going to be using just that substance. We're going to be mixing it with other things. And so as we've seen in the past, we have to consider the dilution that occurs when different solutions are mixed together. And so the actual initial molarity of the S2O8 2- in experiment 1 will be the 0.200 molar, but we use 2 milliliters of it, and we have a total of 11 milliliters of solutions mixed together by the time the experiment is complete. And so we are going to have 2/11 of 0.2 molar is going to be the actual concentration that we start with, the actual initial molarity after the dilution. And so that's about 0.036 molar. So our initial molarity in experiment 1 of S2O8 2- is 0.036 molar. Well, I-, same exact type of thing. Its initial molarity, the stock solution was 0.200 molar, but it's been diluted by the other substances, so its initial molarity due to dilution is also 2/11 of 0.200 molar, which is 0.036 molar. Now in experiment 2, we're going to use 4 milliliters instead of 2 milliliters of the S2O8 2-, So its initial molarity is 4/11 of 0.200 molar, and that's 0.072 molar. And again, this is the real molarity, initial molarity after the dilution occurs. Second experiment, the amount of I2 is 2 milliliters of 0.2 molar, same type of dilution, so 0.036 molar. Third experiment, S2O8 2- is 0.036 molar, and I- is 0.072 molar. So we were either using 2 milliliters or 4 milliliters of the reactants, always diluting by a factor of either 2/11 then or 4/11, and so there are our initial concentrations. So here are our reactions again. The reaction in blue is the one we're going to determine the rate law for. The reaction below that in black is the reaction it's coupled with. And the form of this rate law, before we do anything experimental, we can predict that the form of the rate law will be rate equals K times S2O8 2- concentration to the X power times I- concentration to the Y power. Where K is a rate constant, it'll have a specific value for this reaction at a specific temperature. S2O8 2- to the X power. X is the order of reaction in terms of S2O8. And in our simplified world, X is going to be either 0, 1, or 2. So this reaction will be either 0th order, 1st order, or 2nd order in the persulfate ion. I- to the Y power, same thing. Y is either 0, 1, or 2, and the reaction will be either 0th order, 1st order, or 2nd order in terms of the iodide ion. So to determine the rate law, we need to get our orders and our rate constant. And in order to do this, we need to determine the rate of reaction for each experiment. And the rate of reaction can be expressed in a number of different ways. We can do it in terms of rate of change of S2O8 2-. We can do it in terms of rate of change of I-. Similarly, SO4 2- or I2, we could do rate in terms of any of those. Remember that we have to take into account stoichiometry. So if the reaction, the rate of change of S2O8 2-, whatever that is, the rate of change of I- is twice as much. And so we would have to use that factor. Easiest thing probably here is to do the rate in terms of S2O8 2-. So the rate of reaction in terms of S2O8 2- is change of S2O8 2- with respect to time, and then a negative because S2O8 2- concentration is decreasing, so the rate of change would be a negative value. And then we always make our rates positive, so we put a negative in front. So the negative of a negative gives us a positive rate. Now, the problem is we measure the time for the reaction to occur. We don't know, though, or not very easily, the change of S2O8 2-. But we can use what happens to the I2 to allow us to determine the rate in terms of some other substance. So when I2 is formed in reaction 1, then it reacts with S2O3 2- in reaction 2, and for every one I2 that is formed, then 2 S2O3 2- react. And then remember, we're using a small amount of S2O3 2-, so we're going to run out of it. And then when we run out of it, that's when the color change occurs. So by using what happens to the I2, that it reacts with S2O3 2-, we can change our rate from the change of S2O8 2- with respect to time to the change of S2O3 2- with respect to time. So to deal with the rate in terms of S2O3 2-, we note that for every one I2 that is formed, it reacts with 2 S2O3 2-. So the rate of change in terms of S2O3 2- is twice the rate of change in terms of the rate of change of I2, which is the same as the rate of change of S2O8 2-. And so we put a factor of 1/2 here. Dividing by 2 makes the two rates the same, and we have to, that's our convention. We make the rates the same regardless of which solution we are using for our concentration. And the negative is there because S2O3 2- is decreasing. Now, the reason for changing to S2O3 2- instead of S2O8 is because we know what happens to S2O3 2-. In general, change of S2O3 2- is S2O3 2- final minus S2O3 2- initial. Change of T is T final minus T initial. Initial is when we start our stopwatch timing the reaction, so that'll be 0. T final is whatever time was recorded when the color change occurs, so delta T or T final minus T initial will just be the reaction time. And then S2O3 2- initial, we know its concentration and we know how much it was diluted, so we can determine that. And S2O3 2- final is 0, because remember we had a small amount of this, relatively speaking, and it is all used up when the color change occurs. So this becomes 0. T final minus T initial is T. So what this is going to reduce to is the rate will be -1/2 of negative S2O3 2- initial concentration divided by T. Okay, so here's our form of the rate law again. And what we have just found is the rate is equal to -1/2 of negative S2O3 2- initial. So sometimes we use a superscript 0 to indicate time equals 0 for our initial, divided by T. And then remember that the S2O3 2- concentration when we started the experiment was 0.01 molar, and we used 2 milliliters of it in every experiment, every trial, and in a total solution volume of 11 milliliters. So the 0.01 molar solution concentration is diluted by a factor of 2/11, and then there's the 1/2 out in front to take into account the stoichiometry. And then T is whatever we measure for each experiment. Now, -1/2 of -2/11 of 0.01 molar works out to be 0.000909 molar, and then divided by T. The T will be different in each experiment. The concentration change will be the same. Now, the last thing is how we put our experiments together. We know the concentration of S2O8 2- and I- that we started with in each experiment. We've calculated the rate if you did the steps we just went through, so we calculate the rate for each experiment. And then from the form of the rate law, if we combine or look at experiments 1 and 2, what we note is the rate law was rate equals K times S2O8 2- to the X times I- to the Y. And for experiment 1, we can just put in subscripts for rate for experiment 1, S2O8 2- concentration for experiment 1, and I- concentration for experiment 1, and this is what we get. Note that the rate you calculated, the S2O8 2- concentration we've determined, and the I- concentration we've determined, but we don't know K, we don't know X, and we don't know Y. So we have 3 unknowns, and that seems kind of problematic. But if we note that in experiment 2, we have the same form of the rate law. We know the rate for experiment 2. We know the S2O8 2- concentration for experiment 2. We know I- concentration for experiment 2. And so we have 2 equalities. And if we divide one equality by another equality, we still have an equality. And the purpose for doing this, this is what we do in the method of initial rates. We keep one of the concentrations the same, so I- concentration here was the same, so I- and I- to the Y power, those are going to be the same numbers, so those will cancel out. Similarly, K, the rate constant, is a constant at a given temperature, so K's will cancel out. And so what we end up having is In the second experiment, we had twice the concentration of S2O8 as we did in the first experiment. So we have essentially 0.072 divided by 0.036, so that's a ratio of 2 to 1, and that will be to the x power. And then the rate for experiment 2 divided by the rate for experiment 1 will turn out to be some value, and then that value is either going to end up being closest to 2 to the 0 power if x is equal to 0, if it's a zeroth order in S2O8 or that ratio of rates will be closest to this to 2 to the first power, or it'll be closest to 2 to the second power. Or you can set this up and take the log of both sides and solve for x and see whether x is closer to 0 or closer to 1 or closer to 2. Remember, you're doing an experiment, and so you're going to have experimental uncertainty. It won't be necessarily exactly 0 or exactly 1 or exactly 2. Now, to get the other order, we compare reactions 1 and 3, noting that S2O8 concentration is the same in experiments 1 and 3 and doubled in I- concentration from experiments 1 to 3. So once again, we do a ratio of rate laws, but this time a ratio of rate law for experiment 3 to rate law for experiment 1. We divide, k's will cancel, S2O8 to the x will cancel, and then we'll have the I- ratio, which is 2 to 1, to the y power equals the rate ratio. And once again, that rate ratio will end up either being closest to 2 to the 0 or 2 to the 1 or 2 to the 2, or you can solve for y and see whether it's closer to 0 or 1 or 2, and that gives us the second order we're interested in. Now note, sort of last thing, once you have the order for S2O8 we've determined the value of x. The order for I-, you've determined the value of y. Then we know the rate, we know the concentrations of each substance, we know the values of x and y, so you should be able to solve for k. And then what you would do is solve for k for your data from experiment 1 or trial 1, solve for k for trial 2, solve for k for trial 3, and then average your experimental results to get the overall k. And that's as much as we're going to do on this screencast for the calculations involved in the iodine clock reaction.